So I made a mistake and I accidentally hit stop recording as opposed to pause. So we're going to pick up where the previous lecture left off. We're still in section 1.1. Okay, the next thing we're going to talk about is the um, way that we can read function notation to determine where specifically we are referring to in a two-way table, or how to plug these in algebraically. Now, example 4 is going to show us how this works with a two-way table. So notice we have a quantity which they have listed as capital Q, and this is defined as a function of n. So g of n is the rule that produces Q. It takes n as the input, and it asks us to evaluate g of 3. Now, the way that we can use function notation well is this is going to tell us what number we're using as our input. So g of 3 means find where the input is 3 and then read what the output is. So reading g of 3, we're going to look where n is equal to 3 because it's telling us to plug in 3 for n. You notice that the only difference between the rule at the top, q equals to g of n, and g of 3 is that the g of n has been substituted for 3. So on the n row, we're going to go to number 3, and we're going to look at the output. Output is 7. Next, it says solve where g of n is equal to 6. Okay, so that means that the output is equal to 6, and they are asking you what the n, the input, is, where the output was equal to 6. And you notice there's actually two places where this happens. We have the function, which is q, is equal to 6 at n equal to 2. And we have the function is equal to 6 at n equal to 4. So we need to list both of those n values as our solution to this particular problem. You notice they've given us an answer here, and so on. Okay, in a previous part of the video lecture, I mentioned that a repeating output is allowed in a function, but a repeating input is not. And I mentioned briefly the vertical line test and the horizontal line test. So in example 5, we have these three graphs here. What I want you to look at as you're doing this, and this is not something I'm going to spend an awful lot of time on unless I get a bunch of emails saying, help, I'm confused. And the reason is that this is really a college algebra thing that you do well before you get to calculus. So please make sure that you remember how the vertical line test works. Use it with these three graphs. You can pause the video here, use your pencil if you need to. But the punchline of it is if you can run your pencil from left to right, holding your pencil as a straight up and down object, so a vertical line, you run it from left to right, and it only ever touches the line of our function in one particular place, then that is a function. So if you try that with the circle over here, you'll see what I mean. Anyway, the vertical line test is defined here on page 4. I would make it a point, if you're a notes-taking person, to include this somewhere in a vocabulary portion of your notes. It's very, very important. We need to use this very often before we perform calculus procedures with it, because the calculus procedures are either invalid or they don't work the way that we think that they work if what you're dealing with is not a function. So for example, if we have something that is implicitly defined, which may be like a circle, then the procedure used for doing calculus-based things like a derivative is a little bit different than if you just have a straight cubic function like this guy right here in example number 5. Graphing, the big thing with graphing here, this is an online course. You can use TI-84 calculators for this. Graphing is crutch, is kind of like the most polite way that I know how to say that. You were allowed to do an awful lot of this in your college algebra courses, and I think this is kind of just the way that the world works now, because you can, in fact, like, anybody who tells you you can't do this is lying to you. You can, in fact, get online in almost every single circumstance, and you can, in fact, look up a calculator or something, or get some kind of calculation device to graph these things for you. The reasons why I don't like graphing in the context of a calculus course is that students will try to graph their um, functions that they're working with to attempt to find the key features that you're supposed to be using a manual method, meaning like you got your piece of paper in front of you and a pencil, and the graphs a lot of times, especially in the context of business calculus, as I look through every business calc text I've ever seen, they don't have nice numbers necessarily. So that means whereas on this graph on page 4, you can very clearly see there's a vertex at x equal to 1. Um, you should not assume that just because you graph something on the calculator that it happens at a nice number unless you can prove that it does somehow. And so that's actually what the calculus courses are focused on doing. And so you should not try to use graphing when we have more powerful tests that can identify key features. So you do need to know how to graph, but most of the time, what I want you to understand about graphing in the context of a calculus course is that this is something you do to kind of check your thinking to make sure you're on the right track. It's not something that you do to find your solutions most of the time. Okay. Um, the next thing that they're going to talk about in this functions section is how to express an implicit relationship as a function. What this is saying to do in kind of complicated language is to find a, let's say that a different way. I don't like the way that sentence was forming in my head. Let's say this is like where your high school teachers told you to isolate a variable. Okay. And if they did not use isolate the variable, then the version of this that they probably used was solve for a specific variable. So this particular example is telling you to solve for p. Okay. Well, solving for p means get the p by itself. So there's kind of a lot of ways that we can do this. If you are still having trouble with algebra, like you are not clear on the steps that need to happen to move one thing from one side to the other and get a variable by itself. You need to email me as early as humanly possible, and I will set up a Zoom or something with you, or I will reference you to some of my college algebra material. Um, and we'll get you straightened away on that before we get to the really rough stuff. But the so far as the algebraic steps are concerned, let me just say this now so nobody accuses me of anything later. Um, I will oftentimes skip some things that are understood from college algebra, and that's because my learning targets here are not college algebra learning targets. I do expect that you know how to move the n from one side to the other, and that you know how to divide off the 6 to get the p by itself. Now, this is a review, so I'll just run through it really quick. What we need to do is move the 2n, so we do that by the inverse operation. That was positive 2n, so subtracting 2n from both sides will cancel it off of the left. And then we have a 6p is equal to an expression on the right-hand side, so dividing the entire expression by 6 is how we're going to get the p by itself, because that was 6 times p. Inverse operation of times is division. That will give us that 12 minus 2n all over 6 is our function, p of n, and that's not the simplest possible form from college algebra. The other thing you'll notice about me, especially in a calculus course, especially in a business calculus course, get something that works. I don't necessarily care all that much that it's in simplest possible form. The only place where I do care that it's in simplest possible form is if it obfuscates the meaning of what you're trying to communicate, leaving it a certain way. So if what you have written down is unclear, um, then it needs to be simplified more. Where you're really going to run into this is like the quotient rule. And of course that's not going to make any sense to you right now, but what's going to happen is you get this big long thing, and it's really 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 hard to check to make sure you got the right thing if you don't simplify it all down. It basically requires you to just do the derivative a bunch of times and make sure that it agrees with itself. So just simplify it down when you get to that step. Okay. The second half of this section is all about these, what they're calling toolkit functions. These are the parent functions, okay? So the parent functions, there's actually an entire section over this in college algebra, but they don't talk about as many of these as we're going to use. I think the ones specifically that we teach at A&M, we teach the linear or identity function. So the linear and the identity function are kind of the same thing. Now the reason that they're saying linear up here and identity down here is because constant function is also technically a linear function, in the geometric sense, meaning that it creates a straight line, but it does not have a variable in it. So I don't choose to identify it as linear in its variables because it's actually zero order as opposed to first order, which is traditionally the way that we teach linear functions. So that's just kind of a nitpicky thing that I do, but like you talk to somebody different with a different preference and they'll tell you something different. And it's not wrong. So linear functions is constant and identity function. We do talk about the absolute value in college algebra. This makes V shape. They're grouping these all together as power functions. I'd like you to understand that these are called polynomial functions. They are x to the second, x to the third. Those are the ones that we put into college algebra class. We do talk about the reciprocal function very briefly, but I don't believe that it was identified as a parent function in college algebra until very late. So you may not have made the connection that this was the same as the six basic functions from the parent functions unit, unless your instructor like made it a huge point to do that. I know that I failed in that regard. So it's not it's not rocket surgery. Like you can connect the dots. The reciprocal function is 1 over x. If you want to graph this thing, you can see what it looks like. I don't believe anywhere in the college algebra curriculum we talk about the reciprocal squared function, but this is just like a slightly modified version of the reciprocal. So when you see the graph, you're going to go, okay, that makes sense. We do talk about square root and cube root. The point of these parent functions, I realize I'm going through them and I haven't really told you what I want you to do with these yet. I want you to be able for each of these to just state what the domain of the parent function is and what the range of the parent function is. I'd also like you to be able to just kind of know what the general shape that it makes. In other words, like what do these graphs look like? So when you, whoa, that was bad. I just zoomed way out. Sorry, guys. Um, when you look at the next page here, they've given you a whole bunch of different graphs here. Now, this constant function, they've specifically set this to the constant at 2, but what you need to know is that the constant function is just a horizontal line at whatever constant they've given you. So if they give you -4, the line would be down here at -4. It's that easy. The identity function is a straight line, slope of 1, y-intercept of 0. Absolute value function looks like this. It's a V shape. Quadratic looks like this. It's a U shape. Cubic is this little swish looking thing. Square root is this one-sided deal that comes out of 0 and goes on forever, very slowly. Cube root, same sort of deal, except it's two-sided. It goes up towards positive infinity and down towards negative infinity. The reciprocal is this kind of funny looking crosshair looking deal. And the reciprocal squared, it does exaggerate the curvature of this a little bit, but you'll notice that the effect that it has is it takes the left hand side of the reciprocal function and just kind of like flips it up over the x-axis. Again, the point of that, I want you to be able to state what the domain and the range of all those are by memory. That's like kind of the big deal for 1.1. And the reason for this is that when we talk about the domain and the range, you want to be able to know what the parent function's domain and range is so you know what numbers to change in the interval notation to make it fit whatever function you're looking at. So for example, if I wanted to know the domain of something like 1 over x plus 3. Well, then I know that its parent function is the reciprocal function. So the domain for that is like negative infinity up to 0, and then unioned with 0 up to positive infinity. So I know all I need to do is change the zeros to whatever number matches the function that I described to you earlier. That's that's the point. I want you to be able to do that kind of analysis in your head so that we're not stuck on college algebra standards while we're learning calculus. Okay, whole bunch of stuff about interval notation. I think everybody that I have talked to, every instructor that I know of, does cover interval notation in college algebra. If you were in a course that used Pearson, they require it. And then my open math is really good about doing some of both, but I think the big ones that you had to enter were interval notation. We'd like to use interval notation when at all possible because it is more concise. Okay. A lot of exercises in 1.1, but I think that about covers it. Please email me with problems. Section 1.2, composition of functions and operations. Now, the biggest thing in this section is it has to do with the composition operator, which is this open circle. The biggest thing I want you to know here is that this is not F times G. So if you read this highlighted section here, that does not say F times G of X. What that says is copy down the function f and then replace all the copies of x in that function with a copy of the function g of x. So I know that's kind of crazy, but that's the idea. What they want you to be able to do with this, they want you to be able to understand how functions are composed, because when we get to a portion of chapter two or three, excuse me, I'm blanking on my own course setup, one of the two of them, chapter two or three, where we talk about something called the chain rule. The composition is suddenly very, very important. It's not so much that you need to be able to compose the two functions together, which was a standard in college algebra. You need to be able to identify in what way the functions were composed together using the parent function. So that's really what this is about. And so they have you practice quite a bit with this. I'm going to skip over an awful lot of this because, again, this is a college algebra standard. What I would really like to do for this is all of section two is composing and then shifting the functions around. I don't want to make a huge long video lecture for you guys where you're forced to sit through all this kind of rantatious stuff and you're like, oh my God, skip ahead. And then you might miss something that's important. Because this is the very, very beginning of the review, what I'd like to do instead is have you all email me with what your problems that you're having on this are. And then as soon as I have a few emails a little bit later in the week, this will be closer to Thursday or Friday, what I'll do is I'll actually create a video walking you through how to do those problems. Now, um, please email me if there's any question in your mind. If you are doing these problems and it takes you longer than about 5 minutes to do them, um, write that problem number down and send it to me. And then that will give me a fair list to choose from. And you may not really have a problem with it. It may just take you a little while, but that gives me a list to choose from so I can make a video and then we can have discussions where we need to have them. As opposed to me just like trying to rapid fire blanket everything from college algebra in one section. But that is the end of section 1.2. They want you to know how composition works. They want you to know how to like shift the graphs around. Again, the graphing thing kind of important when we get to later on. You will be able to graph these with your technology for the most part, but I do want you to at least be able to identify the transformations that have happened when they're simple. So far as really complicated graphs are concerned, like cost graphs and marginal cost, that kind of stuff, they're already really weird. So you're gonna either be given one or you're gonna be given technology with which to graph it. It's not going to be something where you have to like plot the points on a piece of paper because they're not nice points. So that being said, remember, please email me if you're doing a problem and it takes you about longer than 5 minutes to do that problem. You need to send that in an email to me. There are not very many of you enrolled in this class, so I need to make sure that you have sent me something so that I can give you something. Nobody emails me. I don't have anything to make. I'm going to assume everybody's good, and then when I get emails and stuff about the exam, oh, I don't get this, I'm going to go back and I'm going to have to say to you, why didn't you email me in the early going when I had the time and opportunity to address this with you as opposed to right before the exam? So, other than that, if you understand that stuff from college algebra, you are pretty good to go on sections 1.1 and 1.2. Please remember the due date on that is the 19th at like 11:55 or 59. You need to look at the course software to see exactly when I have it set to turn off, but it's due on Sunday, before the next week. Another thing, you can expect these video lectures pretty much it depends on when I get to them. It's going to be like Sundays or Mondays. Very rarely, if I have an issue, will it be a Tuesday. I take care of these pretty quickly.